All right, let's talk about voltage sources. The types of voltage sources that we're going to encounter in here are going to be ideal. That means that the voltage is perfect. For example, if we talk about an independent voltage source, schematically it's going to appear like this. It has some voltage value that's given. That V sub S represents a variable that would be the voltage of the source. And it also has a reference polarity. The plus minus indicates the high potential and the low potential side of the voltage source. Now that's an ideal independent voltage source, and those two things must be specified, the polarity and the supply voltage. However, the voltage across this is always going to be V sub S, regardless of whatever it's hooked up to. If it's hooked up to a different circuit somewhere and there are other supplies and there are other elements in that circuit, does not change the fact that the voltage across this is guaranteed to be V sub S and V sub S all the time. So regardless of what current's going through it, V sub S is the voltage of this independent ideal voltage source. Now, when it comes to current sources, they look very similar. The difference is the circle has an arrow in the middle of it that indicates the reference direction of the current. Now, you also have to have the supplied current value given, but those two things are necessary in order for this to be an ideal independent current source. Now, the thing about these ideal independent sources is that they do not rely upon voltages or currents that are elsewhere in the circuit to establish what this supplied value is. Now, that is different when it comes to dependent sources. So now let's talk about dependent sources. Dependent sources are often called controlled sources because they are controlled by a voltage or a current somewhere else in the circuit. For example, let's say that we have a voltage source, and it is controlled by a voltage somewhere else in the circuit. So in other words, the voltage that's somewhere else will be proportional to the voltage coming out of the voltage source. Well, that is called a voltage-controlled voltage source. You can also have a current somewhere else in the circuit controlling that voltage source, in which case that would be a current-controlled voltage source. Now you can have the same thing with current sources. For example, a current source can be controlled by a voltage. So that would be a voltage-controlled current source. But you could also have a current source that's controlled by another current. So current source, current controlled. So a current-controlled current source. Okay, now those are just abbreviations that we've written down here. If you were going to draw these schematically, here's what they look like. They look like a little diamond. There are two terminals coming off. And if this is a voltage source, then it would have a reference polarity inside of it. Now, there's more that's needed here. This would be an example of, let's say, a voltage-controlled voltage source. So the V sub S that's coming out of the supply has to equal something, let's say 3 times V sub X. So V sub X here represents a voltage that's somewhere else in the circuit. Maybe this voltage source is hooked up in a complex network of elements, but somewhere in that circuit that it's connected up to, there is V sub X. And then V sub X, whatever its value is, 3 times that is what V sub S is going to be. So in order to fully specify a voltage-controlled voltage source like this, you need 3 things now. First of all, you need somewhere V sub X defined, and that's somewhere else in the circuit. That's not right here, that's somewhere else in the circuit that V sub X is defined. Then you need this right here. You need the equation that relates the supplied voltage then to that controlling voltage that's somewhere else. And then you also need this reference polarity here. Now, if this had been a controlling, a current-controlled voltage source, then the equation might look something like this, that V sub S, that's the voltage coming out of the supply, this here, is equal to, let's say, 3 times I sub X. And in this case, I sub X is the current that is somewhere else in the circuit, and that current is controlling the voltage that's coming out of this. So this is the equation that relates the two, and V sub S is going to be 3 times I sub X. That's what a controlled voltage source looks like. Now, if we were going to draw a controlled current source, it looks very similar. Once again, diamond shape here, 2 terminals coming off, but inside the diamond is an arrow that indicates the reference direction of the current. And then you have to have an equation that describes what the current's going to be coming out of this. So let's say we talk about a voltage-controlled current source first, then I sub S, that's the current that's coming out of this source, is going to be equal to, I don't know, let's say 5 V sub X. This is the equation then that tells us what I sub S, what the source current is going to be, and it's related to V sub X. V sub X is defined somewhere else in the circuit that this is connected in. So V sub X is defined, and the output current of this current source is going to be 5 times whatever V sub X was. So here we have the current coming out of here as 5 V sub X. So this is a current source that is controlled by a voltage. So this is a voltage-controlled current source. Now, conversely, if we wanted to do a current-controlled current source, then we would have an equation that looks like this. I sub S is equal to 5 times I sub X. In this case, I sub X is the thing that is defined somewhere else in the circuit. So that's a current, and that current controls the output of the source. So we have a current-controlled current source if the defining equation looks like that. We have a voltage-controlled current source if it looks like that. Now, because we can do things like this, because we can have independent sources like these up here and dependent sources like these down here, it is possible to draw a circuit that is considered an invalid circuit. So that leads to this concept of the discussion of valid and invalid connections, or valid and invalid circuits. Let's, for example, talk about a circuit that looks like this. Here I have an independent voltage source, and it has 2 terminals, A and B. And let's connect this up to a dependent current source. And these are connected at their terminals. So they've got connection there, connection there. The 2 terminals of this current source are connected to the 2 terminals of the voltage source. Now we need more information here. We've got the reference polarity for the voltage source. We've got the reference current, but we need to know what is, let's say V sub X is 5 volts. So that is 5 volts coming out of this independent voltage source. And this voltage source is going to be 5 volts regardless of what current's going through it. Now, I sub S, let's call that I sub S, is the current that's coming out of this source, needs an equation that relates it to a voltage or a current somewhere else, and let's say V sub X. So the current here is going to be 3 times V sub X coming out of this dependent current source. So this, it would be a voltage-controlled current source because the output current is controlled by a voltage, V sub X, which is this voltage over here. Now, this may look weird. It's probably not useful for anything, but this is indeed a valid connection. There's nothing wrong with this connection. In other words, there's no contradiction here. The voltage at the 2 terminals here, we could call that terminal A and this would be terminal B here. So the voltage at these 2 terminals is going to be 5 volts. Regardless of where you measure it here, it's going to be 5 volts. So 5 volts across the voltage source is the same 5 volts that's across the current source here. But if you look at the fact that there's one loop here and therefore only one current, that current is going to be, if this is 5 volts, the current's going to be 15 amps. So you have a 15 amp current going around in that direction, the counterclockwise direction there. So the current through this voltage source is going to be 15 amps. Well, doesn't that change the voltage? Nope. It's always 5 volts regardless. And what about this? This is 15 amps going through this source, but it's connected up to the voltage source. Doesn't that change the current? No. As long as this is 5 volts over here, this will be 15 amps over here. So there's no contradiction that's occurring here, so this is a valid connection. Let me show you one that's invalid. Let's say we have the same voltage source here, and its voltage, which we've called V sub x, is going to be 5 volts. And now let's connect this up through its 2 terminals to another dependent source over here. And this one is a voltage source. And let's say V sub s, this is the voltage coming off of this source, is equal to 3 times V sub x. Okay. Now we've got 2 voltage sources here. This is invalid. Now you might say, well, why? Well, let's go back and look at our 2 terminals here again. If I ignore, let's say I ignore the left hand, no, let's ignore the right hand side. So I'm just looking at the left hand side here. And I put a voltmeter across A and B. It's going to measure 5 volts. Okay, guaranteed to be 5 volts there. But now let's say that I look at it the other way. I put my voltmeter here now, and I am trying to measure the voltage across this. Well, V sub x was 5 volts, so if it's 5 volts, then this is going to be 15 volts. So A and B, according to the right-hand side of the circuit, the voltage between A and B is 15 volts, but according to the left-hand side of the circuit, the voltage is 5 volts. So that's a contradiction. The voltage cannot be simultaneously 5 volts and 15 volts at the same time. So what does that mean? That means this is actually an invalid connection. It's not allowed. Now we could obviously draw it because we just did, but it's not valid when it comes to circuit analysis. There's something wrong here, and there's a contradiction in what the voltage should be at A and B, so this is just called an invalid circuit. There are other examples, and there are plenty of examples in your textbook that I think you should look at. There are some connections that are valid that might be beneficial here. For example, let's say that I have a current source connected in parallel to another current source, and maybe even a third current source here. Okay, so all of these are connected, and this would be in parallel. So we'll say this is 1 amp, we'll call this one 2 amps, and this one will be 3 amps here. They all have their reference directions in the same direction. Now, the question might be, what's the current that's coming out here? If they are in parallel, then the current that comes out is just going to be the sum of these individual currents. So this is valid. This is a valid connection like this. Now, if you know anything about series and parallel circuits, these are connected in parallel, you know that things in parallel have the same voltage. So the voltage across all 3 of these is going to be exactly the same. But that doesn't matter to the current, because the current is always going to be whatever it says, 1 amp, 2 amp, or 3 amp here. So I is going to be equal to 1 amp plus 2 amps plus 3 amps. So that's 6 amps is what I is. Well, if one of these had been going in the opposite direction, let's change this one, and let's say its arrow had been going in that direction. Well, now you've got 2 going in the same direction, but you've got 1 going in the opposite direction. So this 2 here would have to have a different sign. It would have to be negative. And in that case, what have we got here? That's 2 amps. All right, but this is a valid connection. Now, you could do a similar type thing with voltage sources. However, you can't connect voltage sources like this if they have different voltages. So if I had a voltage source connected in parallel to another voltage source, and let's put a third one in here as well, and we could say that's 1 volt, this one is 2 volts, this one is 3 volts, and you want to know what is the voltage across these, all three of those. Well, the voltage, because these are in parallel, has to be the same. So this is an invalid connection. It's just illegal. You can't do that because it presents a contradiction. It says the voltage here is going to be 3 volts, but the voltage here is 2, but the voltage here is 1. So this is invalid. It's a contradiction. Now, you can take voltage sources and you can do this. You can connect them in series. So let's say we have 3 voltage sources here, and this is 1 volt, 2 volts, 3 volts. And now I want to know what is the voltage across these 2 terminals here. There. Well, in this case, you're going to add these together, so V is going to be 3 volts plus 2 volts plus 1 volt, 6 volts. Now you can do that with voltage sources because it says nothing about the current. The current's going to be the same through all of these, but the voltages are going to be different. Those 3 voltages will just sum up to be whatever this voltage is here. Now that is valid, but we could make that invalid if instead of voltage sources, if those happen to be current sources. So let's say these are independent current sources now. And I want to know what is this final current that's coming out if that's 1 amp, 2 amps, and 3 amps. Well, according to the rules of independent sources, the current through this is always going to be 3 amps. But the current through this is the same current that passes through this and it's the same current that passes through this. There's only one path here, so the currents have to be the same through all of these. But according to what this one says, the current should be 1 amp. But this one says the current should be 2 amps, and this one says the current should be 3 amps. So that's a contradiction. It cannot be all of those at the same time. So this is an invalid connection. So that gives you a little bit of idea about the difference between a valid connection and an invalid connection. Invalid connections just represent contradictions that cause them to be invalid. Here are 2 other terms I think you need to be aware of, and that is the difference between active and passive elements. An active element is an element that's capable of generating energy. So an active element that's capable of generating energy might be something like a battery, a generator, a wall outlet, an operational amplifier. Those are examples of active elements. That means that an active element is going to have a power that is negative at its terminals. So these are going to be elements that supply energy, or they are at least capable of supplying energy. Now, what's a passive element then? A passive element is just the opposite. It cannot generate its own energy, so its power is going to be positive at its terminals. So there's a difference between active and passive elements, and you just need to be aware of this terminology here. It may come in handy later on. So let's put all these concepts together and see if we can come up with some useful information here. Let's say that we've got a voltage source here that's connected to some element, resistor, capacitor, inductor. We don't know exactly what it is. It's just a black box to us, so we'll just represent it as a rectangle here. And here, let's assign some values. Let's say that's 20 volts plus minus. Let's say there's 12 volt potential across this in that direction. There's an 8 volt potential across that in that direction. Let's say there's a current here which we will call I1, and it happens to be 5 amps. And then this over here, I drew it as a circle. I didn't mean to do that. I'm going to fix it and draw it as a diamond. This is going to be a controlled source. and it is a current source. And since it's controlled, we need to have an equation that relates it to some value somewhere else. So we're going to say it's 0.2 times I1. So I1 here is 5 amps, so this is going to be 0.2 times 5, so 2/10, that's 1/5, so this is going to be 1 amp. So we have 1 amp coming out of that. So what do we want to do with this? Well, let's calculate the powers of everything. Let's figure out which ones are supplying power, which ones are absorbing power for every element, and then let's do a power check and see if everything adds up and we didn't make any mistakes along the way. Okay, well, let's number these. Let's say this is element 1. We'll call this one up here is going to be element 2. This will be element 3, and let's call this one element 4 here, just so we can distinguish between them. All right, well, remember the passive sign convention now. This is going to become important to us. So if I am computing power for element 1, we'll call that P1, then I need to write P equals IV, or I need to write P equals minus IV. Now, which one do I use? Do I use minus IV or do I use plus IV? Well, it depends upon what direction the current is entering this source here. Since that's element 1, looks like the current is going out of the positive terminal here, which means it had to come into the negative terminal. And if it comes into the negative terminal, we need to use minus IV. So minus IV is what we need to figure out the power here. Okay, well, if we plug in the values, that's going to be minus I, which is 5 amps, times V, which is 20 volts. So that's going to be minus 100 watts. So this thing has a negative power, which means what? It means that it is supplying. So this thing is supplying energy to the other elements that are in the circuit. But it is supplying, and we know that because it's negative. All right, well, let's do the same thing for 2. Here's element 2 right here. Look, the current is going into the positive terminal, so that means I need plus IV. So just IV. And that's going to be equal to I, which is I1 in this case, 5 amps, times its voltage, and its voltage is 12 volts. So 5 times 12 is 60, and it's going to be a positive 60 watts. Now, the fact that it's positive indicates that this element is absorbing energy, absorbing power. And it's absorbing energy at a rate of 60 joules per second, which is what a watt is, joule per second. Okay, so we've got 2 of them. Let's do third one, P3. Now look at it. Do I need to write P equals IV or P equals minus IV? Well, you don't know. You don't know which direction the current is going here, because I have a current coming around this way, I have a current going this way. Which direction does the current go? It's possible for it to go any direction, but I'm going to give you this bit of information. So let's say that current there is 6 amps. We've got a 6 amp current going into element 3 here. And look, it's entering through the positive terminal. So that means we use P equals IV. So I is 6 amps and V is 8 volts. So 6 times 8 is 48 watts here. It is positive, which indicates that this is absorbing energy. All right, so we've got all of those right there. We're left with element 4, which is this source over here now. All right, well, in order to figure out the power, do I need to use P equals IV or P equals minus IV? Well, you're not given any information about the voltage over here on this side. Is it plus minus or is it plus minus the other way? We don't know just by looking at this. But maybe there's enough information here in the rest of the circuit to figure out that voltage, and there is. So look right over here. These 2 elements here are in parallel. If they're in parallel, then they have the same voltage. Remember, things in parallel have the same voltage. Things in series have the same current. So these 2 are in parallel, therefore they have the same voltage. So this 8 volts plus minus also applies over here, just like that. It's guaranteed to be that because they're parallel. All right, now look at the current. Well, the current is going in this direction. We're given the reference direction there. So that means the current is entering here through the negative terminal. So I need to write P equals minus IV. All right, well, what is its current? It's minus 0.2 times I1, and I1 is 5 amps, times V of 8 volts. Okay, now 0.2 times 5, that's 1, times 8 is going to be 8 watts, but it's going to be negative. Can't forget that. What does that mean? That this element is supplying. It is supplying energy. It is supplying power. Okay, now notice some things here. First of all, 1 and 4. 1 and 4 are our active elements because they have negative powers. And 2 and 3, those are going to be passive elements because they have positive powers. Okay. Now we've got that figured out. We need to do the power check. Now the power check should work like this. I'm just going to use this space up here. If I take the power for 1, add the power for 2, add the power for 3, and the power for 4, all of that should equal 0. Okay, now does it? Well, P1, I'll go right down here for this. P1 is minus 100 watts. P2 is 60 watts. P3 is 48 watts. And then P4 is minus 8 watts. Okay, does it add up to be 0? Let's see, that's going to be negative 40. That's going to leave 8, and this, yep, it's 0. So our power check checked out. The total power that's being absorbed is equal to the total power that is being supplied. So our power check works and everything is copacetic at this stage. So we can feel confident that we did it correctly at this point. All right, let's move on. Let's talk about the element that we're going to be using throughout most of this class, at least the first half of the class, is resistors. So a resistor is an electrical device, but resistance itself is a property of all matter. It is the electrical property that allows a material to impede a current flow that's flowing through it. Okay, so the resistance itself is a characteristic of all matter. However, if you have a device that has a certain set value of resistance, then that is a resistor, a resistor. A resistor is a circuit element. It's one of the ideal basic circuit elements that we can model mathematically. So that's the difference between resistance and resistor. Now, a resistor is what we're going to deal with mostly in here. So a resistor schematically looks like this. It is wiggly lines that have two terminals. The resistance value must be given to you, so that would represent a resistance value. And the unit of resistance is ohm, OHM. And we symbolize that as a capital letter omega, like that. Now, as I said, a resistor is an ideal basic circuit element, so let's see. What are the three requirements of an ideal basic circuit element? It must have two terminals. Yes, it has two terminals. You must be able to mathematically model it in V and I, and yes, we have a relationship called Ohm's law. V equals IR here. So that's mathematically how we model a resistor in V and I, and it cannot be subdivided. So you can't break this apart and make anything else useful out of it. It's irreducible in that sense, so it cannot be subdivided. So all three requirements for an ideal basic circuit element have been met here. Now, when it comes to resistors, there are two ways to do this. I said V equals IR, and that is true, but it's only true under certain circumstances. So let's scratch that out right there. Look, if I have a resistor here, and I have a voltage across the resistor with a polarity in that direction. And there is a current that goes into that resistor. Let's call that current I. If that is the case, where I have a current entering the positive terminal of a resistor, then it is true that V equals IR. That is nothing but the passive sign convention at work. In order for me to write V equals IR, I have to have the current entering the positive terminal of the resistor. Now, what if it doesn't? Well, if I have a situation like this, where the resistance has a voltage across it, but let's say the voltage is in the same direction, the polarity is in the same direction, but now the current is going in the opposite direction. So the current is entering into the resistor on the negative terminal. In that case, I don't write V equals IR, I write V equals minus IR. All right, so these relationships here follow the passive sign convention, the same as relationships for power did. Okay, now we've talked a little bit about resistance. There is an opposite to resistance called conductance. Now, conductance is useful under certain circumstances. Specifically when you're dealing with resistors in parallel, it may be more useful. However, for the most part, we're going to deal with resistance rather than conductance. But conductance is the opposite of resistance. That's all it is. It's literally, mathematically speaking, the reciprocal of resistance. So conductance, which is symbolized as a capital G in our textbook, is equal to 1 over the resistance. So it's symbolized a capital G, and it's measured in units of Siemens, which is just S. But I've also seen units of mho, and symbolized as just that right there. Conductance is 1 over R. So if you know anything about how resistors in parallel combine, you can see that conductance is just add up, and we'll get to that later. Okay, but you need to be aware of what conductance is. It's just the opposite of resistance. Okay, so if we take resistors and we put them into a network, let's say that we put 3 resistors, and let's put them in series here. So we have resistor 1, resistor 2, and resistor 3. And let's go ahead and hook this up to a source, a voltage source here of V sub S. Okay, now each one of these resistors will have a voltage across it. So if this is resistor 1, it will have a voltage 1 across it, polarity in that direction. Voltage 2, polarity in that direction. Voltage 3, polarity in that direction. Now, since there's only one loop here, whichever direction the current goes, the same current will pass through all of these elements. There's only one path here for, remember what a charge is. A charge is a physical object. It's current flowing through this conductor, these conducting wires, which have no resistance themselves because we're assuming they're perfect wires. But the current that flows through here only has one path, so everything, every element in this circuit has the same current. So we could draw that current and just call it I. So everything has the same currents. Now, here's what you'll notice. These 3 voltages right here will add up. Remember, voltages in series add. So even if they're across a resistor like this, 3 voltages together will add up. And those 3 voltages have to equal the voltage of the source. So voltage 1 plus voltage 2 plus voltage 3 is equal to the voltage of the source. All right, now that's a true statement right there. But based upon our understanding of how voltage and current are mathematically modeled for a resistor, we know that in general, V equals IR. So voltage 1 is going to be I times R1, and voltage 2 is going to be I times R2, and voltage 3 is going to be I times R3. And all of those are still equal to the voltage of the source. So I can factor out the I here, and I have R1 plus R2 plus R3 is equal to the voltage of the source. All right, now look at this. This is very much the same general form as our general statement for Ohm's law, that V equals IR. Well, here we have a voltage equal to I times this, and that's nothing but a resistance. So if we combined all of those into one equivalent resistance, then we have Ohm's law written V equals IR. So if I wanted to take all of those resistors there and I wanted to combine them into one equivalent resistance where I still have the same source, V sub S, and I still have the same current flowing I, then the current that's passing through this will be exactly the same as this up here. So in other words, this circuit here is equivalent to this circuit here, as long as this equivalent resistance is this combination of resistors. So since I have these hooked up in series, if I want to combine series resistances to make an equivalent resistance, then it has to be a simple summation of the individual resistances from I is equal to 1 to N. Capital N represents ever how many resistors there are here in the series. In this case, there's 3. So this is a general statement. If you want to combine series resistors, you just sum them up. And that's the point of this right here. So combining series resistors is pretty straightforward. All right, let's do the same thing for resistors in parallel then. Let's say I have a resistor 1, a resistor 2, a resistor 3, and these are all connected to a voltage source. These resistors, since they are in parallel, are going to have the same voltage. Everything here is going to have the same voltage. So V sub S is the source. It's going to have voltage V sub S. So the voltage right there is V sub S. The voltage right there is V sub S. Right there is V sub S. And right there is V sub S. So everything has exactly the same voltage. Everything, because they're in parallel. Currents, however, not going to work the same. So let's say there is a current going here through resistor 1. We'll call that I1. And this is I2, and this is I3. Now, if all 3 of these combine together, let's say I1 comes down here, at this node it joins up with I2, at this node those two join up with I3, and going in this direction we have one current I. So all 3 of those add together to make I. In other words, I1 plus I2 plus I3 equals I. That has to be the case. But once again, based upon our knowledge that V equals IR, that's a general statement for all resistors. As long as you know the voltage across the resistor and the current through the resistor, that's a general statement. So for I1 here, going through resistor 1, I1 is going to be V over R1. The voltage, remember, is the same for everything, so we don't need a subscript on the voltage. Plus V over R2, that's what I2 will be, plus V over R3, that's what I3 is going to be there. Now, as you can see, I have V's the same everywhere. I can factor that out. So I have 1 over R1 plus 1 over R2 plus 1 over R3 is equal to that combined total I. Now, once again, we have this right here is a general statement that looks an awful lot like this if we solved it for I. I is just V over R. So here I is V over R. If I took all of those then and I combined them together into one equivalent resistance, then it's of this form, V over R equivalent. And that would hold and be a true statement as long as R equivalent is combined this way. Now you notice it's not a straight summation the way it was before. So if I took all of those, combined them into one REQ, and it was still connected up to my voltage source, and I still had the current I flowing that direction, then this Req is equivalent to all of these combined here, as long as 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So in general, then 1 over the equivalent resistance, because if I want to combine resistors in parallel, is equal to the sum of 1 over each of the individual resistances from I is equal to 1 to N, where N in this case is all of the resistors that happen to be in parallel. So this works for resistors in parallel, this right here. So if I want to combine resistors in series, I do it this way. If I want to combine resistors in parallel, I have to do it this way. Now, remember conductance? Conductance, if I knew the conductance of each one of these, then it comes in handy here, and it's a little bit easier rather than this reciprocal relationship that exists here. I could just say, well, the equivalent conductance is just the sum of the individual conductances from I is equal to 1 to N, like that. So if I knew the conductances, then I could do that. But here's the thing. When you go to a store or you order online a resistor, you don't order it by its conductance value so much as you do by its resistance value. Now, I suppose there are counterexamples to that, but for the most part, you're going to end up with resistances on resistors rather than conductances for our examples here. This is probably a more important concept later on in your career of understanding circuits, but for the most part, you see the relationship here, that it's 1 over for G and the individuals, okay? All right, so with that said, we should have enough information now that we can work a problem or two, and we will. But let's talk about power for resistors specifically. We know that in general, power is I times V. Now, that applies as long as we have current going into the positive terminal for a resistor. So as long as we have this situation here, then we can write it P equals IV. However, if we had a resistance and the current is in the opposite direction, so that the current is entering through the negative terminal, we would write P equals minus IV. And in this case, we would also be able to write V equals IR. And in this case, we could write V equals minus IR. Okay, so we're following the passive sign convention when we do that. Now, if you only had, let's say, one of these, let's say that we know what I is and we can substitute in for I, then P equals IV becomes I times V, but V is equal to IR, so we have I squared R. So we can write the power for a resistor as I squared R. And you'll notice here that it's always going to be a positive number for the power for this resistor. Now let me show you that. Over here, let's say we had the opposite case. We're writing P equals minus IV. Well, that means that P equals minus I times V, but V is minus IR. Notice the negative signs are going to go away here, and we have P equals I squared R. So we've got the same P that we had over here for power. So regardless of whether or not we've got the current entering the negative terminal or the current entering the positive terminal, the power is always going to be positive for a resistor. That means that a resistor is always a passive element. It doesn't supply its own energy, it can only absorb energy. If we did the opposite, let's say that we substituted in for V. So P equals IV, and now I, we'll write that as V over R multiplied by V, and we end up with V squared over R. And if you did the same thing over here, P equals minus IV, it's going to be the same. So minus I is going to be V over R, so minus V over R times V, that's minus out front there. And you can see that it cancels and we're left with V squared over R, like that. So it doesn't matter if we've got current entering the negative terminal or the positive terminal. Power is always going to be positive for a resistor. And even if we just use that statement right there, we should still end up with a positive power for a passive element like a resistor. All right, let's throw together a really quick example of this then. So let's say we've got a simple circuit that has a source, and let's say this is a 30-volt source, and this is a 5k ohm resistor. And these two elements then are connected through their terminals, and we could even say, well, there's terminal A and there's terminal B. I don't think we need to label those, but we could if we want to. Okay, well, what are we after here? What are we trying to solve for? The question is, what are the powers? Let's figure that out. And let's figure out the currents. Well, I didn't assign a current direction, but let's say that's given to us, and the current is going around in that direction. That's I. All right, well, if you look here at the source, you can see we've got the polarity that way. That means we have plus minus here at the terminals, which makes this plus minus there as well. And this is the voltage across the 5K. So the voltage across the 5K is got to be 30 volts. And you just found that out, you just figured that out by inspection. Since there's only one element here, the voltage at terminals A and B have to be the same for both elements. So if this is 30 volts over here, it's got to be 30 volts over here. So by inspection, you figured that out right there. Then we should be able to figure out what the current is. Now, look at this element. Look at the 5k ohm resistor here. Do I write V equals IR, or do I need the negative sign here? Well, look at what the direction of the current is. The current is entering the negative terminal here, so I need that negative sign to write V equals IR. So if I'm trying to solve for I, then I is just going to be minus V over R. Okay, well, what's V? That's going to be minus 30 volts over R, which is 5K or 5,000 ohms. Okay, let's do that math. That turns out to be minus 6 milliamps. So our current is that right there. Our voltage is that right there across the 5k ohm resistor. Okay, we've got that information now. Let's look at powers. So let's say the power for the 30 volts. So that's just a subscript to indicate that we're talking about the 30 volt. Well, look, do I write P equals IV or P equals minus IV for the 30 volt source? Current's going around this way. It's entering in through the positive terminal, so I just write P equals IV. Then when I plug in my numbers, I is negative 6 millis multiplied by V, which is 30 volts. Okay, so it's going to be 180 millis, and the unit is watts. So, I forgot the negative sign. There's a negative sign there. So it's negative 180 milliwatts for the power of the 30 volt source. And that negative indicates that it's supplying power. So that makes it an active element. Now let's do the same thing for the 5K resistor here. All right, now you might say, well, do I need P equals IV or P equals minus IV? Well, if I'm going to use that equation, I need P equals minus IV. Let's go ahead and work this out. P is going to be minus 6 milliamp times the voltage of 30 volts. So that turns out to be positive 180 milliwatts. So I figured out That's the power of the 5K ohm. But let's say we wanted to use one of the other equations. Let's use I squared R. Now, the negative sign doesn't matter in this case, so we don't have to worry about it if we use I squared R. So that's going to be I squared, that's going to be minus 6 milliamps squared times R, which is 5,000 ohms. And that turns out to be 180 milliwatts. Hey, so either one of those will give you the same answer. All right, then let's try the other one. Let's try V squared over R. Well, voltage across this was 30 volts, so 30 volts, quantity squared, divided by 5,000 ohms. Let's do that math. 180 milliwatts. So regardless of what we use, we end up with the same answer. And notice that it's positive. And since it's positive in all cases, that means that what? That it's a passive element. All right, now we do the final check. It should be that the power for the 30 volt source plus the power for the 5K should sum up to be 0. And obviously it is. Negative 180 plus positive 180 is going to be 0. Okay, so we did power check. Everything works out just fine. So with that, let's stop this video and we'll pick up here next time.